So what we're going to do right now is we're going to take this to be the definition of the logarithm. And if we do that, then I claim that we can read off the properties of the logarithm just about as easily as we could before. And so I'll illustrate that now. And there are a few other examples of this where somewhat more unfamiliar functions come up. This one is one that in theory we know something about. The first property of this function is the one that's already given, namely its derivative is 1 over x. And we get a lot of information just out of the fact that its derivative is 1 over x. The other thing that we need in order to nail down the function, besides its derivative, is one value of the function, because it's really not defined, specified by this equation, only specified up to a constant by this equation. But we nail down that constant when we evaluate it at this one place, L of 1. And there we're getting the integral from 1 to 1 of dt over t, which is 0. And that's the case with all of these definite integrals. If you evaluate them at their starting places, the value will be 0. And together, these two properties specify this function L of x uniquely. Now, the next step is to try to think about what its properties are. And the first approach to that, and this is the approach that we always take, is to maybe graph the function to get a feeling for it. And so I'm going to take the second derivative. Now, notice that when you have a function which is given as an integral, its first derivative is really easy to compute. And then its second derivative, well, you have to differentiate whatever you get, so it may or may not be easy. But anyway, it's a lot harder in the case when I start with a function to get to the second derivative. Here it's relatively easy. And these are the properties that I'm going to use. I won't really use very much more about it than that. And qualitatively, the conclusions that we can draw from this are, first of all, from this, for example, we see that this thing is concave down every place. All right? And then to get started with the graph, since I see I have a value here, which is L of 1 is equal to 0, I'm going to throw in the value of the slope. So L prime of 1, which I know is 1 over 1, that's reading off from this equation here, so that's 1. And now I'm ready to sketch at least a part of the curve. So here's a sketch of the graph. Here's the point 1, 0, that is x equals 1, y equals 0. And the tangent line, I know, has slope 1. And the curve is concave down, so it's going to look something like this. Incidentally, it's also increasing, and that's an important property. It's strictly increasing. That's because L prime of x is positive. And so we can get from this the following important definition, which again is working backwards from this definition. We can get to where we started with the log in our previous discussion. Namely, if I take the level here, which is y equals 1, then that crosses the axis someplace, and this point is what we're going to define as E. So the definition of E is that it's the value such that L of E is equal to 1. And again, the fact that there's exactly one such place just comes from the fact that this L prime is positive, so that L is increasing. Now there's just one other feature of this graph that I'm going to emphasize to you. There's one other thing which I'm not going to check, which you would ordinarily do with graphs. Once it's increasing, there are no critical points, so the only other interesting thing is the ends. And it turns out that the limit as you go down to 0 is minus infinity. As you go over to the right here, it's plus infinity. It does get arbitrarily high. It doesn't level off. But I'm not going to discuss that here. Instead, I'm going to just remark on one qualitative feature of the graph, which is this remark that the part which is to the left of 1 is below 0. So I just want to remark, why is L of x negative for x less than 1. Maybe I don't have room for that, so I'll just put in here x less than 1. And I want to give you two reasons. Again, we're only working from very first principles here, just that the property that L prime is 1 over x and L of 1 is 0. So our first reason is that, well, I just said it, L of 1 is 0 and L is increasing. If you read that backwards, if it gets up to 0 here, it must have been negative before 0. All right, so this is one way of seeing that L of x is negative. There's a second way of seeing it, which is equally important, and it has to do with just manipulation of integrals. Here I'm going to start out with L of x and its definition, which is the integral from 1 to x dt over t. And now I'm going to reverse the order of integration. This is the same by our definition of our properties of integrals as the integral from x to 1 with a minus sign, dt over t. All right? Now, I can tell that this quantity is negative, and the reason that I can tell is that this chunk of it here, this piece of it, is a positive number. Right? This part is positive. And this part is positive because x is less than 1. So the lower limit is less than the upper limit, and so this is interpreted, the thing in the green box is interpreted as an area. It's an area, and so negative a positive quantity is negative. Minus a positive quantity is negative. All right, so both of these work perfectly well as interpretations, and it's just to illustrate what we can do.